Hello everyone, welcome to your EEE 4504 experiment number 2. So in this lab we're going to be looking at half wave and full wave control rectifiers using UJT, SCR, DIAC and TRIAC. And today we're going to be using the Proteus software, which you should be familiar with. For today's lab, the objectives are firstly to observe a half wave control rectifier and its corresponding wave shapes. For that we're going to be using an SCR. Next, we're going to observe a full wave control rectifier and the corresponding wave shapes using SCR, UJT, and diode. And lastly, we're going to be observing a full wave control rectifier and its corresponding wave shapes using TRIAC and DIAC. So as I mentioned, we're going to be studying controlled rectifiers, right? So when we hear the term control, we should associate that with SCRs and TRIACs, right? So these are some of our control devices. Hence, we insert the term control for a rectifier. And what is a rectifier? A rectifier is basically a device that converts AC to DC, right? So that is the purpose of a rectifier. Or, in other words, we're converting bidirectional voltage or current to unidirectional voltage or current, right? So that's what we refer to as AC or DC. Now, if you consider a simple half-wave rectifier, right? So half-wave rectifier circuit using a diode. We have our V input, we have a diode, and we have a load resistance R that we measure our voltage out across, right? So if we supply a voltage like this at our input, right? So if this is our input voltage at the in our simple half-wave rectifier, then the output voltage will be somewhat like this. The diode will conduct during the positive half cycle, so we're going to be observing this output across our resistor. And it will block the negative half cycle, so we will have no output during our negative half cycle, right? So this is the wave shape that we'll get at our output, and because we're converting the bidirectional current to unidirectional, we're calling it a rectifier. Now, if we, instead of using a diode, if we change this to a SCR, right? So if we insert an SCR here, where this is our gate terminal, and we supply a gate current IG here. So what if we recall from our last lab, how does an SCR function? An SCR turns on when we supply a gate pulse. Okay, so it does not turn on before that. We can control when it turns on using the gate pulse. So for example, say that I'm supplying a gate pulse at time alpha and then at time 2 pi plus alpha, right? So this is the instance that I'm supplying a gate pulse. That means the SCR will start conducting in this region only. Okay, so it will block the negative region because it has to be forward. So if you recall, the two conditions that are required for turning an SCR on, firstly, it has to be forward bias. So this region, it will not turn on. And secondly, we have to supply gate pulse. So we're supplying a gate pulse at time alpha and time t2 plus alpha. So the SCR output, or the output across the resistor, will be something like this. It will not conduct before we supply a gate pulse. Then when we supply gate pulse, it will start conducting. And we will observe this output across our resistor, right? During the negative half cycle, it will not conduct at all because it is reverse biased. Then during the positive half cycle, it will wait until we supply a gate pulse at time t2 pi plus alpha. Then it will start conducting. So we're getting an output sort of like this. Now, the reason we're calling it control is because we control the time, or when we supply the gate pulse, we can control how much area will be under the voltage curve, right? So this is corresponding to our average voltage value. So what I mean is, if we supply the pulse at this instance, right, this will be, we will get an output like this, and this will be what our area under the voltage curve, or our average voltage is. But say if we change, or if we supply alpha at a later instance, so say we're supplying a voltage at alpha prime, right? So this is what alpha prime is. Then the SCR will conduct after we supply alpha, or after we supply the pulse at alpha prime. So this will be the output, right? We will get an output like this. And when we have output like this, we will see that the area under our voltage curve has reduced, right? So the average voltage that we're getting has reduced. So we can use control devices to control the magnitude of our output, or not the magnitude, the average value of our output voltage, right? So that's why we're calling it controlled rectifiers. Now, when we associate devices like the SCR or the triac, we need to provide a pulse, right? We need to provide an IG to turn that on. The pulse will be somewhat like this. So we will have a very short pulse of high magnitude that will turn our device on. Okay, so this will be our pulse or our gate current, right? So this is required to turn the device on. So we need to know what ways we can provide this gate current, right? So in this lab, we're going to be looking at two triggering circuits. So we're going to be looking at the UJT triggering circuit, that we're going to use for our SCR, and we're going to be looking at the diac triggering circuit, that we're going to be using for our triac. Okay, so these are the two triggering circuits that we're going to be using in this lab. So I'll give you an overview on that first before we proceed to the lab. Okay, so let's start with the UJT triggering circuit. Okay, so before going to the triggering circuit, we should know what a UJT is, right? So UJT stands for unijunction transistor. So it's a transistor. And so another transistor that we should know of is the BJT, right? So that's another type of transistor. Now, whereas BJT, that is mainly used for amplification, right? So that's what it's most known for. UJTs are generally used for on-off switching, so or triggering circuits like triggering of circuits that are used for SCRs or triacs. The structure of the UJT, it's basically a three-terminal device. So we have two bases. We have a base 2, we have a base 1, which are both N-type, okay, and we have a P-type emitter. These are the three terminals in a UJT. If we look at it from a structural point of view, we have an N-type block, right? We have an N-type block where we have our two base terminals. We have our B1 terminal and our B2 terminal, and we have a P-type emitter terminal, right? So we have a P-type emitter terminal. And a UJT has an equivalent circuit somewhat like this. Okay, so between our base 2 and our emitter, we have a resistance RB2, and between our B1 and our emitter, we have a resistance of RB1. So these two resistances, they form a voltage divider network. So okay, so this is basically a voltage divider network between the two base terminals. Now, at the emitter side, you remember that the emitter is P-type emitter, right? So because there is a junction here, right, this is because there is a PN junction there, we can represent this PN junction by an ideal diode. Okay, so from the emitter to the two bases, we have an ideal diode, and this represents the PN junction. Okay, so this is the structure of our UJT. So how does this UJT function? Okay, so let's say this is our equivalent circuit of the UJT, right? So we have our RB2, we have our RB1, we have the diode for the emitter side. What we normally do is we supply the input through the emitter side. Okay, so this is where we insert the input, and we bias the two bases. So we bias base 2 and base 1 with the voltage VBB. Okay, we bias it in such a way that B2 is positive with respect to B1. Okay, and we connect the B1 terminal to the ground. Okay, so B1 is where we connect to the ground. Now, consider the case when we supply no input voltage, right? So when an input voltage of 0, then the voltage across RB1. So if we represent as VB1, that's going to, using voltage division, we can find that VB1 is equal to what? The voltage across, the resistance RB1 divided by the total resistance, which is RB1 plus RB2, RB1 plus RB2, multiplied by the bias voltage, right? So multiplied by VBB. So using simple voltage division, we can say that VB1 equals to RB1 divided by RB1 plus RB2 into VBB. Now, this term RB1 divided by RB1 plus RB2, we call this eta. Okay, so we represent this as eta, where eta is the intrinsic standoff ratio. So we can also say that VB1 is equal to eta VBB. Now, if we supply an input to the emitter terminal, right, there will be what is the condition? So when will the current will flow when this diode is forward biased, right? But the current will flow in this direction, right? So it will flow towards the ground. Now, for the diode to be forward biased, we have to keep in mind that there is a resistance across RB1, right? Before we insert the input, and that is equal to eta times VBB. So for the diode to be forward biased, the voltage across the input must be greater than this eta times VBB, or the voltage across RB1. So this is one of the conditions that we have to fulfill. Once the voltage across the diode is greater than, or the input voltage is greater than the voltage across RB1, the diode will become forward biased and it will start conducting, right? So there will be a current flow, IE, through the from the emitter to the base 1 terminal. Okay, so one thing you have to keep in mind is the associated RB1 resistance, right? This is due to the N-type, this is a characteristic of the N-type material. And for PN junction materials, what happens is, so for example, consider a PN junction, right? What happens is we have a P-type material and N-type material, we have a junction between them. And once we, this junction we can think of as a resistance, right? So say we have resistance R across this junction. Once we apply voltage, say a certain amount of voltage that exceeds the potential barrier, right? This potential barrier breaks down and current starts flowing through the PN junction. So the resistance that we had associated with the PN junction, it reduces to a very small value. And this occurs due to an injection of charge carriers, right? Similarly, when we have current flow from the emitter to the base 1 terminal, we have an injection of charge carriers into the base region, right? So we have an injection of charge carriers into the base region. This will cause the resistance RB1, so RB1 resistance, to drop. Okay, so the RB1 resistance will drop significantly because we have an associated injection of charge carriers. Now, what do we expect in a normal scenario? So if we have an increase in current, so if the current IE increases, right, what will happen? If we think of it normally, if there is a normal resistance there, then the voltage across RB1, that will be equal to IE times RB1, right? If IE increases, we expect VRB to increase. However, when RB increases, when IE increases, RB1 drops significantly, right? So instead of increasing, VRB1 decreases. So with an increasing current, we have a decrease in the potential, right? So we have a negative resistance. What do we call negative resistance? Negative resistance occurs when the current increases but the voltage decreases. So something that does not follow Ohm's law. So in this case, we're having that where even though the current is increasing, we have a decrease in voltage. So we have a negative resistance associated with this, right? And that is what we're going to use to create our triggering circuit. Okay. Again, if the input is reduced to below, so if the input is reduced below eta VBB, right, RB1 will start increasing. So the thing you have to keep in mind with the UJT is that RB1 is variable, right? It's not fixed. RB1 is variable and is dependent upon IE. So what I mean is when IE starts flowing, right? When we apply voltage across the emitter terminal that is greater than the voltage across or eta VBB term, right? Then the resistance RB1 will decrease. However, when we reduce the voltage back to below eta VBB, the resistance RB1 will decrease. So that's because we're having reduced injection charge carrier. So RB1 depends upon the injection of charge carriers or the current flowing through the emitter terminal. Now the characteristics of the UJT look somewhat like this. So if this is our emitter voltage and this is our emitter current, right? Current across the emitter, then there is a point up to which the current will not flow, right? So this is our eta VBB point. Once we exceed this point, the current will start flowing from the emitter, right? And initially it will behave normally. So as current increases, the voltage will increase. But then we will reach a peak point which we call V peak, after which even though our current is increasing, the voltage will start decreasing. The voltage will drop significantly, right? And this is known as our negative resistance portion. And this is the portion that we are actually interested in for this lab. After it reaches a minimum value of valley point, okay, so we call this a valley point. After the voltage reaches the valley point, the UJT will become saturated, and then it will start functioning normally. Okay, so the resistance the voltage will increase with increasing current. But this portion of negative resistance from the peak point to the valley point is what we're interested in, and that's what we're going to use to create our firing circuit or our triggering circuit. Okay, so now let's have a look at our UJT triggering circuit. Okay, so in our triggering circuit we have our UJT, right? So this is our UJT with our base 1 and base 2 terminals. We have a variable resistance, we have a capacitance, and we have a resistance R1 across which we will take our output or triggering pulse values. Okay. So how this works is the capacitor C is charged through the variable resistance. Okay, so the capacitor C is charged through our variable resistance. When the capacitor is charging, the voltage builds up in the capacitor, right? So we have our voltage building up. And once the voltage across the capacitor reaches a value of the peak voltage, so the peak voltage of the UJT, right? Peak voltage associated with the emitter of the UJT, the emitter will start conducting heavily. Okay, so the emitter will start conducting heavily because the RB1 of the UJT will fall to a very low value. And when this occurs, when the emitter starts conducting like this, so there will be current flow across here, right? And then the capacitor will discharge through the emitter. The capacitor will start discharging through the emitter. So it will discharge through the resistance R1. It will discharge through this resistance. One thing you have to keep in mind is the resistance of the discharge path. Okay, so when it is discharging, because we have reached our peak value of the voltage of the UJT, our internal voltage of the UJT falls to a very low value, right? RB1 falls to a very low value. So the resistance of the discharge path is much lower than the resistance of the charging path. Okay, and this means the capacitor will discharge much more quickly than it charges. So if we have a discharge time like this, a charging time like this, our discharge time will be very quick. It will be only this duration. And this resulting, so the discharge is very fast, right? So we can call that a pulse. So we can associate that with a pulse. And this resulting pulse of current through R1 is used to trigger our SCR or triac. And again, since the discharge time of the capacitor is short, the current will have a relatively high peak, so that's what we want, and a very fast rise time. So it will be a pulse. So we will create a pulse that we're going to use to trigger our SCR. Okay, so when the capacitor is discharging, okay, so when the voltage falls below eta VBB, so this is that point in our UJT where the current will stop flowing, right? So once the capacitor reaches this point, it begins charging again through the variable resistance. One thing you can keep in mind is that we can alter the value of the variable resistance. That will change the time it takes for the capacitor to charge, right? So if we control the time it takes for the capacitor to charge, we can control the frequency of the firing pulses. This will become clearer a bit later. So let's look at this, right? So what we're saying is the capacitor starts charging through the variable resistance. once it reaches the value of V peak, okay, it's the V peak value of the UJT at this point, it discharges very quickly. It discharges very quickly through the emitter and through the resistance R1. Okay, and then it reaches this point where or eta VBB, right? So this is our eta VBB point where the current stops flowing. So the capacitor again starts charging. It charges and it gets to the V peak point again, and then again it discharges to the V off point. So this is how it goes. And then this portion of time that it discharges, right, this is when current flows through R1, the resistance R1. So in the resistance R1 we have a peak like this, we have a peak of voltage like this, which is corresponding to the pulses that we will use to trigger our SCR circuit. Now, what I said previously, if we change the value of the resistance, right, we can control the frequency of the pulses. So that is associated with the time constant of our capacitor. So, for example, we can make it so that the capacitor charges faster, right? And if it charges faster, the discharge time won't change. So the discharge will be same, and then it will charge again, and the discharge will be same. So our pulses, right? These pulses, they will be coming at a much higher frequency. So instead of this time, right, we are getting frequency of this time. So that's what I mean by using the value of the resistance to control the time it takes or the frequency of the firing pulses. So this is our UJT triggering circuit that we're going to use for our SCR, right? I hope it's clear. If it's not clear, you can ask questions during the review class. Okay, so now let's move on to the diac triggering circuit. Okay, so what is a diac? A diac basically means diode alternating current. Okay, so similar to the triac, if you remember the structure of the triac, what was it? It was two SCRs facing opposite directions. The diac is similar. The diac is basically two Zener diodes. So instead of SCRs, we're using Zener diodes facing opposite directions. So because it's diodes, not triacs, we have only two terminals, right? And it's bidirectional. And similar to the triac, we have an MT2 terminal and an MT1 terminal. So the way the diac works is it basically conducts. Okay, so it's basically a Zener diode that conducts after avalanche breakdown. So in both positive and negative half cycles, so if we supply a bidirectional current, right, it will break down the Zener diode facing the forward direction in the positive half cycle and again in the negative half cycle. So it conducts after we reach avalanche breakdown. And the advantage of this is that conduction can be stopped simply by reducing the voltage below avalanche breakdown point. So the characteristic of our diac will be somewhat like this. So in the positive half cycle, we'll have a blocking state, right, when the voltage is blocked. Then it will reach the breakover or avalanche breakdown point, after which the diac will start conducting heavily, right? So it will start conducting very heavily. And it's similar in the negative direction, right? So we have a breakdown point, and then after which it starts conducting heavily. So one thing to keep in mind is, so in this portion where it starts conducting, right, we can see that even though the current, so this is the current and this is the voltage, the current increases, right? So the current starts increasing, but the voltage is decreasing. So this portion of the curve is again associated with a negative resistance, right? So as we observed in our UJT case. So this negative resistance is what we're again going to use to create our triac triggering circuit. So let's have a look at that now. Okay, so this is the structure of our diac firing circuit or diac triggering circuit. Similar to the UJT case, we have a variable resistance, right? We have a capacitor, and that is connected to our diac terminal, and the other terminal of the diac is connected to the gate terminal of our triac. Okay, so and this is our triac. So similar to the UJT, the capacitor is charged using the variable resistance. Okay, but the difference here is this happens for both positive and negative half cycles. So this is because the diac is a bidirectional device. Okay. So once the value of the capacitor or the voltage across the capacitor, the charging voltage, exceeds the breakover voltage of the diac, so the avalanche breakdown point of the Zener diodes in the diac, it discharges. Okay, sorry. So this should be discharges. it discharges very quickly through the diac. So discharge again is much quicker than charging because of negative resistance, right? So the same case. And hence we create pulses, right? We create pulses that we're going to use to trigger our triac. And similar to the UJT, the variable resistor can control how fast the capacitor charges, and hence we can control the frequency of the pulses. So just one thing to keep in mind is that because the diac is bidirectional, so the capacitor charges in the positive direction, it reaches the avalanche breakdown point, right? Then of the diac, then it discharges very quickly through the diac. And then during the negative half cycle, it again charges in the negative direction, right? It reaches the negative breakdown voltage, and then it discharges quickly through the diac. So we create pulses in both the positive and the negative direction, and this can be applied to a triac because the triac can take pulses from both positive and negative currents. So that concludes the two firing circuits that we're going to use in our lab today, and that is our theory portion. If you have any questions, please ask in the review class. So now let's move on to our circuits in Proteus.